All right, in this screencast, we are really going to dive into color and how we go from light to color. You'll notice in this screencast that there is going to be a little bit more text on the slides. I know we're getting to the end of the semester and everyone is tired, so that's why there's a little bit more text on the slides right now. Okay, so let's jump in. When we first talk about like how we go from light to color, we can't really get started until we talk about Isaac Newton. So this is an illustration of Isaac Newton, and there's the light, and it goes through the prism, and then it's broken into these different colors. And originally, Newton kind of created these artificial categories that we learn now. He chose 7 colors because he wanted the visible spectrum to parallel the number of notes in the musical scale. Now, it's interesting here because some references say he wanted it to parallel the 7 days it took God to create the world from the Bible, right? So different sources kind of give us different reasons, but the 7 that he kind of these artificial distinctions he made were red, orange, yellow, green, blue, indigo, and violet. Now, in some modern day sources, the colors named in the rainbow differ from Newton's because they have removed indigo, right? So they've said, look, indigo and blue, those are redundant. We're just going to call that area blue. So that's what we see there. Now, let's talk about wavelength and color. So how is wavelength related to color? So at the turn of the 19th century, a fine fellow named Thomas Young, you can see his picture there, was another English scientist, and he was able to demonstrate what other scientists had hypothesized, that light, like sound, is a wave. Now, the color of a particular light wave is determined by its wavelength or frequency. Now, wavelength varies inversely with frequency. And a color, though, is typically referred to only by its wavelength. Okay, so as a review, a wavelength is this area from a point on the wave to an identical point on a second wave. There is the wavelength. The frequency is in a certain amount of time how much or how many waves pass a point. And so when we look at this, B right here is the higher frequency, right? Because more waves have passed in this kind of amount of time. And so you'll notice it also has a shorter wavelength. And so that's what we see there with both of those things. Now, let's talk about the visible spectrum, right? When we look at this visible spectrum, we see wavelength increasing as we go this way. From gamma to X-rays to ultraviolet, we have visible here, infrared, microwaves, and radio frequency. And then we have frequency increasing this way. So inversely means as one goes up, the other goes down. So that we see that inversely relationship there. Now, the range of light from red to violet that we saw in a rainbow that's visible to the human eye is called the visible spectrum here. And it's really just a tiny portion of the electromagnetic spectrum, which is shown here. The only reason we have a name for the visible part is because our particular anatomy is responsive to these particular wavelengths of light. Now, and that's human. That's our human wavelengths of light. One of the things that's interesting is, right, so Homo sapiens here can see from about 400 to 700 nanometers, but other animals are different. And so the animal that they think has the broadest amount of wavelengths is the mantis shrimp. So it can see from about 300 to 700 wavelengths. If this is and this is some of the publications that have investigated this. If this is something you're interested in, there is a podcast named Radiolab on NPR, and they have a color podcast, and they have two of these. So they have a color, and then they revisit color. And those are, if you've got about an hour or so, those are really interesting podcasts to listen to because they talk about the in and outs of different animals and how much color they can see. Now, when we talk about color and wavelength for us, we have violet light is about 380 to 450. Blue light is from about 450 to 490. And this particular one puts indigo in there, which is fine. Green light is about 490 to 570. Yellow light's about 570 to 590. Orange light is about 590 to 630. And red light's about 630 to 750. Now, so how does this light that we see turn into color? So the process of light turning into color can be broken down really broadly into 4 steps. In the first step, a spectrum of light is emitted from a source. Now, that source can be all sorts of things, right? It can be the sun, it can be a light bulb, right? Any of these, the fire, anything, right? And that light strikes an object or material or surface, and some of the light is absorbed or some is reflected. And remember, we've used the word scattered for reflected as well. So we're using those interchangeably. Now, some of the wavelengths then are detected by our visual system. And then there's this psychology of perception where the mechanics of our particular brains determine the color that we actually perceive. Now, although these steps sound simple, the process is actually quite complicated, and it becomes quite complicated here at step 4. We take in a whopping amount of information and try to make the best sense of it, all while not becoming overwhelmed. So our visual system uses a whole host of cues to help us determine the colors we see. Now, the light reflected at us from a particular point is just one of these cues. And as we try to make sense of the objects in front of us, we have to construct their shapes, the light source that's illuminating them, the wider visual field in which they sit, and the colors that fill their boundaries. So there's a lot going on there in step 4. Now, when that light hits our eye, it stimulates a part of the brain called the retina. Okay, and so I have a picture of an eyeball here, and you can see the large part here is the retina. Now, it's in the retina where color perception starts. So you have a thin layer of cells about the thickness of a credit card at the back of the eye, right? And then the retina is actually made up of brain tissue that separates from the brain during the development of a fetus, but remains connected to the brain via the optic nerve, right? So we're right in here. That's where our optic nerve is. Now, the retina performs the first most important step in visual information processing in that it responds to the light that hits our eyes and turns that light into neural signals. And then the brain interprets that. So inside the retina, there's a number of different kinds of photoreceptor cells that send these impulses to the rest of the brain via the optic nerve, right? And we're going to talk about rods and cones in just a second because we've got both of those. Now, the eventual result of all this is a world of color during the day and then shades of gray at night. Now, so let's talk about rods and cones. So rods are photoreceptor cells that are in our retina. That allow us to see in the dim light and the dark. We only have one type of rod, but there's approximately 120 million of them within each of our retinas. Rods dominate when there is very little light available at night or in a dark room, when little to no color is visible, and we see mostly blacks, whites, and grays. Now, These rods are highly sensitive to small amounts of light and changes in light. So the sensitivity that even just one photon can be detected, so sensitive that even one photon can be detected. Now, your eye detecting one photon is like feeling one microscopic speck of dust landing on your skin. So it's pretty amazing. Now, what are the cones? So the cones are receptor cells in our retinas. That allow us to see color. Right? So despite the fact there are only 3 different types of cones versus only one type of rod, there are far fewer cones than rods, with only 1 cone for approximately every 20 rods. Now, unlike rods, cones dominate in the daytime or bright light. Let's just make sure we have a note up here that these are dominant in the dark or at night. Okay. They also differ from rods in that they allow for really high sharpness of perception in our vision, but are not sensitive to small shifts in light. Cones on their own don't tell us what colors we're seeing. The signals from cones are processed further by the retina and then transmitted to the rest of our brain and eventually translate them into the perception of color. And sometimes this doesn't go as smoothly, right? So some people can experience synesthesia. I had a student one time who was traveling in the car with her mom and said, "Ooh, Mom, this is a really colorful song." And she was seeing colors that were associated with music. And that's just where some wires had gotten crossed. And she was able to put a color with certain musical notes, which is kind of interesting. Now, so we have 3 different types of chromes, which is called trichromacy. We have L cones, which are sensitive to longer wavelengths of light in the visible spectrum, right? And these a lot of times are synonymous with red cones. We have M cones that are sensitive. So we've got our L cones here. We have our M cones here, and these are sensitive to the green, the medium wavelengths of light in the visible spectrum. So a lot of times they're called the green cones. And then we have the S cones here, which are sensitive to shorter wavelengths of light, and those are our blue cones. So these are the 3 cones that we have that are active. If you are missing one of the cones, that's what results in color blindness. So that's all the biology that we're really going to cover about why we see color. But one of the things that you may be thinking is, hey, Dr. Pierce, when I put on makeup in fluorescent light, it looks a lot different than when I put on makeup in a natural light or when I walk outside, right? And you'll hear people talk about, oh, fluorescent lighting is so harsh, and go on and so forth. And so from that, like just observation, we recognize that colors look different depending on the light source. So when we change the light source illuminating an object, the object will reflect different wavelengths of light, and it causes the color of the object to change. Now, there are 2 kinds of light sources. There's incandescent and luminescent. Now, incandescent light is created by heat. So that's the sun. So for example, the sun, that can be fire, or tungsten lamps a lot of times. So tungsten lamps are incandescent light. Luminescent light is not heat-based, right? And examples here are things like fluorescent lights, LEDs, which you find in monitors or televisions. Now, the luminescent light source only emit light from parts of the visible spectrum. So these only emit light from part of the visible spectrum. Whereas incandescent light, right, emits all of the wavelengths from the visible spectrum. Right? So depending on the kind of incandescent or luminescent light source present, those number of wavelengths reflected back from an illuminated object can be limited or expanded, and that changes the color that we see. So the light that a surface reflects is dependent on the spectrum of the light illuminating it. If an object absorbs light from a source with a wide spectrum, like daylight, it will reflect more wavelengths. So if an object absorbs light from a source with a wide spectrum, it will reflect more wavelengths, right? And therefore look more colorful to us. So let's look at the picture of these candies here. So these are the same candies that have just had pictures taken in different lights. So the top here, these were photographed in daylight, right? And we can see all of the different colors, right? Now, if an object absorbs light from a source that emits more light from one end of the spectrum, then more light from that end may be reflected. So look at the second photo here, right? This was taken under red and green theater lights. Okay. Now, the red and green light does cover most of our visible spectrum, except for blue and violet. And that's why the blue there appear to be dark green, okay? And so if we kind of blow it up there, you see that what we would consider, so these right here, that was the blue candy, right? And now it appears to be green because we only have the red and green wavelengths that are hitting it. Now, if an object absorbs source from a light with a super limited spectrum, it may reflect fewer wavelengths. So let's look at this last image here. This image of these candies, the only light that's on it is a yellow laser with a really narrow wavelength of 589 nanometers, right? So just one really narrow area of that electromagnetic, the EMR, the electromagnetic radiation spectrum. Now, only yellow candies appear yellow. There's no other wavelengths for the light to reflect. So everything else is has the yellow undertones that are coming through, or they're appearing to be brown, right? So the yellow candies there are the only ones that are reflecting that light, that appear yellow, their correct color. So light does affect the colors that we can see. Now, so what are our primary colors? When we talk about colors, what are the primary colors? A primary color is just a set of colors that when combined produce a wide range of other colors. So these are just a set of colors that when combined produce a wide range of other colors, right? Contrary to what most of us are taught, there are no absolute primary colors. The designation of what a primary is arbitrary and is changed depending on the prevailing ideas about color and vision, as well as the pigments available at the time. So, for example, when I was growing up, the primary colors that I was taught was red, green, and blue. I went to a workshop a couple years ago, and there was a person at the workshop who was very passionate that those were no longer the primary colors, and the primary colors were yellow, magenta, and cyan, which are the primary printer colors. I don't really care one way or the other, right? This is not something that I feel passionate about. So we are going to follow the convention of most of the color theory that's taught today in naming the primaries. And we're going to break it up into either light or pigments, right? Or paint. Okay. And so the primary colors for light, right, are considered right now to be red, green, and blue. And you can see if you mix those, what they give you. If you mix all of them together, you should get white light. Okay. Now the primary colors for paint, we're going to go with magenta, yellow, and cyan. All right. And so those are the three primary colors for paint. Now you'll notice that when you mix the primary colors for paint, you get black, but when you mix all the primary colors for light, you get white. The reason is because these go through different mechanisms when they're mixed. So let's look at light first. Light undergoes additive color mixing. Now, additive color is a system that describes just how the colors of light mix together. So let's go how the colors of light mix together, right? This is the basis for how color is created on computer screens or TVs, the colors emitted from LEDs, a stage light in theater, or any other kind of light source. So when light travels to our eyes, our retina add it together in different wavelengths that our cones are sensitive to and compares the activity in each. And that result is the perception of a particular color within the visible spectrum. When all the colors are added together, they turn white. Right, and you can see kind of the color wheel here, but these are three flashlights, and they're all together. When they're mixed, they turn white. Now, when we mix paints, or pigments, that is a subtractive color mixing. So subtractive color is a system that describes what happens when light comes to us indirectly because it hits a surface first. So some of the wavelengths of light are absorbed or subtracted by the surface, and some are reflected back into our eyes. The subtractive color system is the basis for how pigments are mixed. And so you can see, this is an example here. We've got all of these light sources coming in. This is red is reflecting back. We're mixing them here. We end up with black, and then we've got some kind of paint colors here that are mixed. So when we think about this, imagine a white light hitting a surface. White light's made up of all the colors in the visible spectrum. When the white light hits a surface, some of the colors in the visible spectrum are absorbed and others are reflected back to our eyes. When a color is subtracted from white, another color is revealed. So if the surface subtracts red wavelengths from white light, we see cyan. If the surface subtracts green from white, we see magenta. If the surface subtracts blue from white, we see yellow. If all of the colors are subtracted, then no light is reflected and we see black. So when we talk about subtraction, we're also talking about absorption, right? All those colors are being absorbed. So light hits the pigment in this paint can right here. Every color in the visible spectrum is absorbed except for red. And so that's why we see the red light, okay? Other things to consider when we talk about color is hue and value and chroma. Hue represents a color without reference to how dull or saturated or dark or light that color is. And it corresponds to wavelength. Right? So when we talk about the wave, right, and the different wavelengths, hue, that is the wavelength. Now, value is also known as brightness, right? And that's the term used by artists to describe how light or dark a color appears. Right? And it corresponds to the amplitude of the wave. Remember, amplitude is shown here. It's the distance from about half the wave to the top, right? And then we also talk about chroma, and chroma is also known as saturation, right? And this is how pure or saturated a color is. The color becomes less saturated or duller as its complements added. So how pure or saturated a color is, right? And so the way you make a color duller or desaturated is you add its complement. And so you're muddying. You're muddying it up. So for example, this is a blue hue at various levels of value. So when we talk about value here, we are going from, this is a very low value to high value, right? With the blue. This is a blue hue, so same wavelength, but at various levels of saturation, right? So this is really saturated, and then this would be what we would consider desaturated. So we've mixed in a little bit of the complement there, and it's desaturated. Now, we've talked about the light spectrum, and maybe you're sitting there and you're like, Dr. Pierce, the colors that we see there, those 7 colors of the spectra that Newton gave words to, that's great, but my favorite color is pink, right? And it's not on there. What's the deal with that? Well, right, those would be non-spectral colors. So the mixing of individual wavelengths in the visible spectrum results in the visually diverse scene just around us, right? And all the different colors we see. And so mixtures of those wavelengths are called non-spectral colors, right? So mixing individual wavelengths gives us a variety of colors called non-spectral colors. We've got a lavender, for example, on here. These include your pinks, your purples, your dull colors, think like a dusty rose, your dark colors, your light colors, and even your grays and your whites, right? And so that when we think about this, that also includes pastel colors. So black is the absence of all visible light. In terms of pigment, black is the absorption of all visible light so that no light reflects back to our eyes. White objects, on the other hand, reflect the full spectrum of visible light. Now, pastel colors are a subcategory of non-spectral colors because they're actually a combination of every color in the visible spectrum reflected into our eyes, but at different intensities. So here's an image, right, of a pink surface. Here's all of the light wavelengths, and they're reflected back, but at different intensities. So the red intensity here is much higher, and that's why we end up kind of with this pink here. Pastel light and pastel pigments are created in the same fashion, generally by adding white. In the case of pink, most of the light reflected into our eyes is red, and the rest of the light reflected is white light. And so it's the mixing of that pink or the red with the reflected white light which shows up as pink for us. Now, I mentioned before one of the ways that we can desaturate a color is using its complementary colors. Complementary colors are two colors that neutralize each other. So these are two colors that neutralize each other. If the complements are made of light, they make white light when they're mixed. If the complements are paints, they make a neutral color when mixed. Desaturating or draining the color of the mixture used, a lot of times turning that mixture brown, right? So if you want to mix a brown, you take green and mix it with red, for example. Now, color wheels are really helpful because they place complementary colors across from each other. Now, where we see this in cosmetics is complementary colors are used to cancel out or neutralize unwanted tones on the skin. So, for instance, if you have ever seen a green concealer and wonder, what is that for? Right? A green concealer can neutralize redness from things like acne. An orange or pink or peach concealer can help neutralize blue or purple under eye circles, right? So if you've got under eye circles that are blue or purple, it can help with that. And then a purple concealer can counteract like yellow tones. So if there's some yellow tones there, that's what a purple concealer can do. When used in like eyeshadow, complementary colors can make the colors of your eyes appear more vibrant or intense. So for example, reddish browns, right, and purples tend to make green eyes pop. Blues and purples make brown eyes appear more intense because brown is just really dark orange, right? So that's what we see there. And then of course, orange, browns, and golds can make your blue eyes seem more intense. Now, although there's a debate about where they start and end, red, orange, yellow, green, and browns are generally considered to be warm colors. And violet, blue greens, grays are generally considered to be cool colors. These categories of warm and cool colors, as they're referred to in art and design, are not scientifically based. In fact, they are the opposite of scientific color temperature scales, where red is at the cool end and blue is at the hot end. The colors we associate with warm and cool colors come from our emotional associations with natural phenomena. Artist and color theorist Joseph Albers challenged the notion that blues were always cool and reds were always warm. This is from one of his books. He shows that cool pinks and reds alongside blues, and then some warm blues, right, alongside some pinks and reds. Joseph Albers was really into color context, right? He said that colors are informed by the things they're around. And so a really good example of this, and this is also from his book, is that the red here looks more vibrant on a black background than it does on the orange background, even though these reds are all the same color. And so the context, or what the color is next to, informs our eye of how that color looks. Now, you already intrinsically know that. if you've ever looked at color cosmetics. And if you go out and look at color context for color cosmetics, you're going to see a lot of different things. And so, for example, one of the color companies that I buy from always has, if they've got a new color that comes out or any color, they always show it on different skin tones so that you can see what the color looks like on the skin tone. And this is a really great example. That is a beautiful green right there. I can barely tell it's green here, right? So we are informed by the colors that are around the color we're interested in. And so here's an example of 3 different skin tones and how the colors look different on each one. You'll find things out there like, what works best with eye color. A lot of times this is based on those complementary colors. And then there's an area of thought that everybody is broken up into like different colors that work for them, the spring, summer, winter, and autumn. And therefore the cosmetics, the colors that look best on their skin tone, which is just kind of interesting. So this idea of color context really drives the marketing for some of these colors. Now, the last thing we're going to talk about here in this screencast is, can color affect your mood? And the answer is kind of yes and no. There's very little research on how the brain responds to color. Now, we do respond to color in 3 different ways. The first is our biological response. We do know a bit about how we respond biologically to red objects. They can inspire fear. We also know some things about how we respond biologically to blue light. It can help us with everything from seasonal affective disorder to issues with our internal clocks to problems with concentration. The second is our cultural response. So, for example, in the West, blue is far and away the favorite color, and yellow is the least favorite color. Whereas if you go east, yellow climbs to the top of the charts where it's everybody's favorite color. And those differences have to do with the cultural associations with the various colors. Now, the third is our personal association with color. A scientist or psychologist, Alexander Schoch, in the late 70s, made a claim that has now been debunked that says pink will calm prisoners. And so a lot of prisons were painted pink. So if you went to prison and you had to live in a pink cell, then you may never want to see pink again, right? It's a real turnoff for you. But maybe you grew up in a pink bedroom in a loving, supporting household, then you may gravitate towards pinks, right? It's always interesting when we talk about color and how it affects our mood. It also affects marketing. And so in the late 90s, early 2000s, purple ketchup came out. Heinz came out with like a purple ketchup and a green ketchup, with the idea that they would sell more because kids would be more attracted to kind of these bright, fun colors. That was not the case. Everybody thought that was really gross. The feeling there was ketchup should be red, right? And so we had a very specific color emotional response to when that ketchup color got changed, which was just kind of interesting. All right, so you can take a whole class on color. So this was really, we just dabbed our toe into color and what it is. In the next screencast, we are going to talk about pigments that are specific to cosmetics.